Hi, everyone. Thank you, Dr. Munzer. There's going to be a Q&A as soon as we get through this at the end of this session with Dr. White and Dr. Orchard. But first, I have a distinct pleasure of bringing up here a wonderful colleague and associate who's been with us for many years, Leslie Renato, who is the director of our family support programs and our Pathways program, who's going to present a very special award to Dr. Paul Orchard.
Hello, everyone. It is my privilege to be the one to stand before you today and present our Legacy Award for Clinical Practice to a man whose work has literally reshaped what it means to catch MPS in time. Dr. Paul Orchard is the medical director of the Inherited Metabolic and Storage Disease Transplantation Program and a professor in the Department of Pediatrics in the Division of Blood and Marrow Transplant and Cellular Therapy at the University of Minnesota. For decades, he has devoted his career to a single, relentless question: how do we get treatment to a child before the disease can take anything from them? His clinical and research work centers on hematopoietic stem cell transplantation and other cell therapies, including gene therapy, and how we can improve outcomes for patients with inherited metabolic diseases. He has spent years studying how to get enzymes past the barriers that have stopped so many treatments before, to the brain and to the peripheral nervous system, for patients whose bodies simply don't produce the enzymes they need. He has worked to refine stem cell transplant approaches and combination therapies, and he has helped build the multi-institutional cooperative studies that let our small, rare community pool our data and our hope across state lines and institutions. But I want to tell you about the piece of Dr. Orchard's work that means the most to us, because it sits at the very heart of what the society exists to do. Dr. Orchard is the reason so many of our families get the diagnosis before the damage is done. He has led the charge at the University of Minnesota to expand newborn screening for MPS, because we all know that with these diseases, time isn't just important, it's everything. A diagnosis at 6 months instead of 6 years can be the entire difference between a child who thrives and a child who never gets that chance. And he didn't stop at his own institution's doors. Every other year, he brings together geneticists, pediatricians, public health leaders, and rare disease researchers from across the country for MPS newborn screening meeting, a gathering he built specifically to keep that gateway open so more states, more labs, and more families have access to early detection. We have had the honor of sitting in that room with him, working alongside him as the society pursued its own newborn screening nominations for MPS 1 and MPS 2. Dr. Orchard doesn't just attend those meetings, he drives them. That is the kind of legacy we are here to honor today, not just a body of research, but a body of work that reaches directly into the lives of families before they even know they need him. I'd like to thank him personally for all the emails and connections and for being available to patients and families quite literally worldwide. If you are a patient, a family member, clinician, care provider, or anyone else directly impacted by Dr. Orchard's work, I'd love for you to raise your hand so we can look and see how many people have been touched by him. Thank you all. So it is my honor, on behalf of the National MPS Society and every family whose child was caught early because of the doors Paul Orchard has pushed open, to present this year's Legacy Award for Clinical Practice to Dr. Paul Orchard. Dr. Orchard, please join me.
Wow, thanks very much for that very gracious introduction, and thanks to the MPS Society and everyone here for inviting me to speak today. It's humbling to be here with some of our colleagues, esteemed people in the field and with all the families that are here have been touched by the MPS disorders, and many of the patients who are here with us as well that live with some uncertainty and difficulties on a day-to-day basis. So we recognize what you're going through, and there's a lot of uncertainty in the future, but hopefully we'll have things to be able to offer families down the road that are going to be more effective, and that's what I'm going to talk about a bit today. So my disclosures, so we work with some of the companies that help us with clinical trials. I don't have any direct support, but we are always interested in being able to move things forward and figure out what the next things to offer are going to be. So Joe actually showed the same figure, I think, here. I think my slide looks better, but so anyway, if you want to borrow it down there. You know. So, but it's an important concept, and Joe talked about it in terms of the rationale for giving enzyme therapy, but it's also the rationale for giving cellular therapy. So essentially, yeah, the cells accumulate glycosaminoglycans, which is kind of on the y-axis there, and then if you put cells in culture that are normal cells with the cells from patients with Hunter-Hurler in this circumstance, that accumulation of the glycosaminoglycans goes away, essentially. So this is what was termed cross-correction. And it was really the rationale for considering transplant. So the idea was, and this goes back to the 80s, actually, or this observation was published in '68, I think, but it led us to consider using bone marrow transplant as therapy. So the idea is if you could take cells, blood cells, from someone who's not affected, that are going to make enzyme, and you can transplant those into somebody who's deficient, those blood cells are going to circulate through the body for the life of the patient and serve as a source of enzyme. So that was really what got transplant started. And the first patient that was transplanted was for MPS I, was done actually in Bristol, in the UK, and reported in Lancet in '81. But essentially, they showed that the glycosaminoglycan, in this circumstance, it was the mom actually who was the donor. But they could show that you could alleviate some of the accumulation of the storage material. And so this is really what launched treating lysosomal diseases with blood stem cell transplant. But now we know what all the enzymes are, and you know what the genes are, and so you can take these genes and introduce them into cells and make pharmaceutical grade enzymes. So why are we still talking about doing transplant for these kinds of disorders? So again, the thought is if you have a cell that's missing enzyme and you do a blood stem cell transplant, there are cells that are going to produce enzyme, and the cells are going to take that up and utilize it. But importantly, if there's cells within the central nervous system that also are not making enzyme, and you can get some cells into the brain after a blood stem cell transplant that are donor cells, those cells can also serve as a donor for enzyme for the cells that are deficient. So because the enzyme replacement therapy, those molecules are very large, they don't penetrate into the brain very well. And so that's why we're still doing transplant for these diseases. So it's primarily for the diseases that have a neurologic manifestation to them. So this is a pie chart with the lysosomal disorders, and the ones in red here are the ones that have a neurologic component to them. And these are the ones that we're transplanting. So again, it's primarily at this point with the standard transplant procedures that we're using, it's the kids that have neurologic disease that are the ones that we're transplanting. So, and this is information about the untreated MPS I patients and what happens neurodevelopmentally if you don't have any intervention, that these patients lose a significant amount of ground. And this was published by some of our colleagues in Europe, but I think it's important to kind of understand as we're talking about different types of therapies, One of the choices might be how effective is the therapy. One might be what's the risk of a particular kind of therapy, and potentially, depending where you are, costs may play a role here too. But essentially, in this publication, on the left side there, if you're diagnosed with MPS I, you're young, assuming you probably have more severe disease, those patients will go on enzyme and then you get transplanted. But the fork of the road here is that those are the patients that are going to have neurologic disease. The patients that aren't going to have neurologic disease, so the Shea patients, are on the right side. So those patients are just going to go on enzyme and stay on enzyme. So this is the big fork in the road, at least for MPS I. If you've got neurologic disease, you go on a transplant pathway, generally speaking, and if you aren't predicted to have neurologic disease, then you go on enzyme and stay on enzyme. So Julie Isengard, who was one of our group, published this a few years ago. So as enzyme therapy became available, some of the families, and again, we started doing transplants for MPS I back in the 80s, but as enzyme became available, some of the families decided just to go on enzyme and not get transplanted. So in terms of the untreated MPS I patients, that's this curve on the bottom, most of those patients didn't survive past 10 years of age. But you can see that what the survival is on the transplant side, which is on the upper part of this. But those that went on enzyme and stayed on enzyme didn't do as well as the patients that were transplanted. So this suggests that actually transplant is better therapy in terms of helping with survival and potentially some of the somatic and other types of issues that the patients have. But it's because of the risk of transplant that we're not treating the patients that have attenuated disease and don't have neurologic disease. So I just wanted to walk through a bit about what the role of transplant is for some of the various MPS disorders. So we'll talk about MPS I first. So if you have Hurler, generally the standard of care is to go on and get a transplant, assuming you can find a donor and these other things. The attenuated patients, though, we don't generally do for the reasons we just talked about. So those patients we would assume are not going to have neurologic disease, although we have looked at spinal fluids, and some of these patients have attenuated disease and their GAGs are still high, despite having attenuated disease and despite being on enzyme therapy for 15 or 20 years. So, you know, these are, it's kind of a continuum. It's not black and white in terms of whether you have attenuated or severe disease. But anyway, most of the patients that are attenuated don't go on to get transplanted. You know, and I think Joe asked me at one meeting, how good would your outcomes need to be with transplant before you would do the attenuated patients? And that's maybe not for me to decide. The MPS II patients, we don't generally do transplant for the MPS II patients. Most of these patients go on enzyme and stay in enzyme, and now we've got other enzyme therapies potentially offer them. Most of the data suggests that transplant works better for MPS I than it does for MPS II, than it does for MPS III. So we could talk more about that a bit, but 70% of the Hunter kids have a neurologic component to their disease, and so if you can identify them very early, you've got a better shot at potentially making a difference with transplant, but transplant isn't curative from that standpoint, clearly. I was just going to mention that in Japan, where MPS II is a bit more common, they've done a fair amount of transplants for MPS II. And actually, the data suggests that these patients do quite well. Their GAGs are a bit better with transplant than they are with enzyme therapy. You know, whether their MRIs progress or not is probably not incredibly important. But their sense is that transplant actually may be better therapy for MPS I than for the standard enzyme. For MPS III, as we were kind of talking about, transplant generally isn't done, doesn't seem to be as effective, and I wish I knew the reason for that. I think part of it is that there's a very limited number of donor-derived cells that make their way into the brain. So we can't replace brain tissue with bone marrow transplant. The microglial cells, which are or cells that look like microglia, can be derived from blood cells, but there's only about 15% of the brain that are microglial cells, and we only probably get 5% of those that change. So we're in the 1% ballpark in terms of how many cells in the brain are now donor. And so we're just on the cusp, I think, of whether we're able to accomplish what we want. And I think you may need more cells for MPS II than 1 and MPS III than 2. So I don't know what that limitation is, but that's my sense, is that we probably would just need to be able to deliver more enzyme to get the better outcomes. For MPS IV, again, we don't generally do transplants for MPS IV patients, although because there's no neurodevelopmental problems, we don't rationalize taking the risk of transplant. Although there are groups that have done transplants for MPS IV, and it suggests that they may have a bit better outcomes than they get with enzyme, but again, it's a relative risk question. We used to transplant the MPS VI patients, but again, they don't have the neurodevelopmental issues, and so generally we haven't been referred to transplant or an MPS VI patient for transplant for a number of years. 7, there's not a lot of information. The animal data suggests that it might be helpful, but we have other things to do for MPS 7 now too, so we don't get those referrals really either. And I just wanted to mention ICEL a bit, because we've transplanted a number of patients, not a large number of patients, but enough patients with ICEL to unfortunately show that transplant doesn't seem to help. And the biology of ICEL is a bit different, because the mannose-6 phosphate pathway that we were talking about, which is important to have the enzyme get back into the cells, is really the issue here. So it's different than the other lysosomal disorders. And I want to talk a little bit about where we are with transplants. So Liz Bronlund is one of our cardiologists, and her group pulled this data together. So we went back to some of our patients we transplanted way back when. And so there's a pretty steep curve there, as you can see, in the first year. There's a lot of patients who didn't make it through transplant. But the curve isn't flat. Some of these patients are still dying, 10, 20 years out after transplant. And we don't have a ton of data in terms of what they're dying from. We think it's still cardiopulmonary types of problems, primarily, but they generally aren't with us when they die, and we don't necessarily hear what happened. But the way we're doing transplant now is not the way we were doing transplant back in the 80s, and because a lot of patients got total body irradiation in that time frame, when we're talking about patients that are 25 years out, for instance, and we don't do that anymore. So, I'm hoping long-term outcomes are going to be better, but still, transplant is not curing these patients, clearly. And this looks at the surgical procedures that the kids that have gone through transplant for MPS I still have to have happen. So, Clayton's going to talk about some of these things too, but they have carpal tunnel problems. A lot of the kids need to have that procedure done. They have kyphosis and back issues. They have hip and knee issues, and cord compression is less common. But despite having gone through transplant, people still run into disease-related issues. So again, we're not fixing people. So in talking about, the term allogeneic transplant means you're getting somebody else's cells. So there's still safety issues. And I usually tell the families it's about a 10% chance your child isn't going to survive transplant. And if the kids are sicker, that makes a difference. If we don't have a good donor, that makes a difference in terms of relative risk. Although we were just going back and looking at our data. So we've refined our transplant protocols over the years. And one of the last big changes we made was in 2015. So we've done 44 transplants for Hurler kids since 2015, and we only lost one of those. So, It's gotten a lot better. We have better antivirals and better antifungals, and there's 20 plus million donors that we can go to now, so you can generally find a decent related donor. There's hundreds of thousands of cord bloods that we can access that we didn't have, years ago. So things have gotten better, but still, people get sick. There's a patient on the floor now who got veno-occlusive disease and hasn't gotten out of the hospital yet. There's one that just got back to Tennessee yesterday, or I think a couple days ago. That family was with us for 6 months. Had graft versus host disease issues. Actually, the patient that died out of that 44 died of graft versus host disease. So there's still complications associated with transplant. One of the other limitations too is we think more enzyme is going to give us better outcomes, but there's no way to turn the dial up in terms of how much enzyme you're delivering with transplant. We just don't have the capacity. Whatever the donor cells are making is whatever the donor cells are making. So that's a limitation as well. So how can we do better? I'm going to stay in my lane and not talk about this. Joe talked about this, and so I'm not going to go there. But there are new enzyme therapies that are being developed. Being able to identify these kids early makes a huge difference, and newborn screening piece, as Joe again alluded to, makes it really important to be able to identify the kids. So in that group of patients from 2015, we had, I think, 11 that were transplanted at less than 6 months of age, primarily because they were newborn screen. I think there was a couple of patients that had older siblings there too, but none of those, we haven't lost any of those kids. So newborn screening is going to make a huge difference. Can you deliver more enzyme though? And we can't do that with our standard transplant pieces. So, this is kind of where the gene therapy part comes in. So I'm going to talk a little bit about the gene therapies that are currently available. So one of the ones that Orchard Therapeutics was doing, and it's not my company, I always have to say when we do these talks, but so this is it's a different approach. So you're using the kid's own blood stem cells instead of using somebody else's. So there's a procedure, kind of starting on the left there, there's a procedure where we do an apheresis, meaning we collect the kid's own blood stem cells. Those cells are shipped to the laboratory. There's a virus that's got a normal copy of the gene that's introduced into the blood stem cells. They're frozen down, and then after the quality control piece suggests that everything went well, then they let us know. It takes about 6 weeks, and then they let us know, and the kids come back. They still have to get chemotherapy because we have to eliminate the blood stem cells that aren't making enzymes so you can replace them with those that are. And then you can check and see how these kids are doing. So this is kind of a platform. This is we call ex vivo, meaning the cells are engineered outside the body, lentiviral-based gene therapy. So this protocol that I was talking about was for MPS 1. The MPS 2 one that's happening, I think it's actually on hold. I think they need to get more virus to be able to move forward. But there's an MPS 2 study that was done in Manchester and MPS 3A as well, but it's essentially the same protocol. So Immusoft and our group have been working together. So this is a different means of doing the gene transfer. So that was a viral approach, and this is with a transposon and transposase. So the transposase makes a double-stranded break in the DNA and then cuts out the iduronidase gene for the MPS 1 patients. That's the population that we're treating right now. So it's non-viral, should be less expensive, assuming things move forward and gets licensed down the road. And the integration is supposed to be more random, so it's less likely that you're going to end up with leukemias or those types of things. But this is essentially what that looks like. So we still have to do apheresis, but here instead of collecting the blood stem cells, we're collecting the B cells. The B cells get shipped off, and the nucleic acids are introduced with electroporation. So apparently, so the way that they do it is they pass electric current over the cells, and then cells can pick up the transpose on a transposase. Again, the cells have to be checked to make sure that the procedure went well. But then you get your cells back, but there's no chemotherapy here. So that makes life a lot easier for people. So the kids are admitted, well, actually they're adults, so we started with adults, but they get admitted to the hospital overnight just to make sure that there's no problem with infusion, but then they're back out. So no chemotherapy, no immune suppression associated with this, but there have been I keep saying kids, there's been 3 patients that have been treated, and I think the 4th is going to get treated here pretty soon. So this is the Regenix Bio approach that Joe mentioned as well. So this is an in vivo gene therapy, meaning you're delivering the virus in this case to the patient. So there's a pocket of spinal fluid in the back of the brain called the cisterna magna, and this is an adeno-associated virus instead of a lentivirus, but essentially you can put the virus into that spinal fluid. The spinal fluid is supposed to circulate through the brain and then potentially provide a source of enzyme. So this is another gene therapy approach that's being explored for both MPS I and MPS II, and then potentially other diseases down the road. So this is another so this is the Ultragenyx approach. So this is, rather than putting it directly into the spinal fluid, it's given intravenously, but this is an adeno-associated virus approach as well. So, and the AAV viruses can stimulate an inflammatory response, so the patients have to go on immune suppression. But there's no chemotherapy associated with it, but you have to be on immune suppression for a period of at least months. So I swiped this slide from Don Cohn, who's a gene therapist, but I like the concept of this. There are tremendous amounts of things that we're going to be able to offer, I think, down the road that we have not been able to offer before. A lot of these are going to be clinical trials relatively in the short term, but some of these things I think are going to get licensed. And hopefully we'll be able to have an opportunity to better treat the patients that have the MPS disorders and other lysosomal disorders and genetic disorders. But we've been relying, for instance, I'm a transplanter again, and we've been doing this for a long time, but we need better things, clearly. And so second generation enzymes, gene therapies, other approaches may be helpful, and maybe combination approaches are going to be more helpful than one approach alone. So I initially trained on the oncology side. There's not a lot of silver bullets on the oncology side that you can use one chemotherapy and it's going to cure whatever cancer you have. And maybe we're going to end up having the same type of approach for some of the MPS disorders as well. So just to close, transplant has still remained some of the best therapy for some of these disorders, but I think these things are potentially going to change. Transplant still remains associated with relatively high risk. Being able to identify these patients early is key, and we're committed, as are number of other institutions around the country and internationally, to trying to figure out what's the next best thing, essentially. So, and gene therapy is here, actually. It's not arriving, it's already here. What's going to work best and what approaches are going to be less toxic and all these things we're going to have to work out over a period of years, but I think we're going to be able to better control some of these diseases than we've had the opportunity to in the past. So I will stop there.